So here, we've got a diving board, length L, it's anchored to supports at one end, and a distance L over 3 from the same end. Mass of the diving board is M. Find the force exerted on the diving board at each point where it's attached to the supports. So what forces do we have acting on this diving board? Well, we have gravitational force. Since it's uniform, that means the mass is evenly distributed, so the gravitational force we can treat as acting in the middle. It always acts at the center of mass, and since it's uniform, the center of mass is in the middle. And then we have forces from each of these two supports. So one might assume that those forces, they're both going to be exerting an upward force. I'll call that N1, and I'll call that N2. And, alright, in order for the diving board to hold still, well, then we need to be in equilibrium, which means that net torque is going to be 0, net force is going to be 0. Now, as always, we can set the pivot point wherever we want to. I will choose to put my pivot point at the left end here, because that force from that pillar is something we don't know. Setting my pivot point there means that the torque from this guy is going to be 0. So, net torque equals 0. What do we have? Well, we've got a gravitational force acting that would tend to rotate the board clockwise, so that's a positive mg. It's acting a distance L over 2 from my pivot point, and it's acting at 90 degrees to the diving board, so sine 90 is 1. Got a normal force. If it's acting upward, that would cause the board to rotate this way, which is counterclockwise. That's minus, and the torque from that one is going to be N2 times the distance, L over 3, and that's also acting at an angle of 90 degrees from the board. And those are the only two forces supplying torque, so that equals 0. Then doing some quick algebra, we can see that N2, let's see, an L cancel out, and then we would have to multiply by 3, so it's going to be equal to 3 halves mgl. The force from the second pillar, it came out to be positive, so it's that much force acting upward. Okay, then we can write our net force equation. We've got these two forces from each of the two supports, and then we've got gravitational force acting downward, and those have to add up to 0. So we can then use our result from part 1, N1 plus 3 halves, I'm sorry, L canceled out, so it's not 3 halves mgl, just 3 halves mg. And some quick algebra, we learned that N1 is going to be minus 1 half mg, which tells us that the force that one's exerting is actually downward, which might seem weird, but this is actually how it works. If you have two supports and the center of mass is out to the side, this one exerts an upward force, this one exerts a downward force. If we think about what would happen, say we set our pivot point right here. Well, gravitational force would cause the board to rotate this way, clockwise. If this force was upward, it would also cause the board to rotate clockwise, so it wouldn't stay in place. So this force then has to be downward to exert a counterclockwise torque to make the net torque equal to 0. So if you do have a diving board structured like this, this support, this exerts an upward force, it's holding the board up, while this one, it's bolted down, and the bolt is actually exerting a downward force on the diving board. And here's another example. We've got a uniform bridge of mass 17,000 kilograms and length 20 meters, supported by pillars at each end. So pillars, bridge. A car is 8.5 meters from, or sorry, this is length 20 meters. And we've got a car, my beautiful car, you all know I'm such a great artist, is 8.5 meters from one end. Determine the force applied to the bridge by each pillar. Again, so what forces do we have acting? Well, we've got the bridge, uniform, so it's right down the middle. We've got mass of bridge times g. we've got the gravitational force of the car times G, and then we have probably upward support forces from each of these two pillars. Where do we want to set our pivot point? We can pick anywhere we want, but we know this force, we know this force, we don't know either of these two, so it's wisest to set your pivot point at one of these two supports. I'll set it on the left just because. Yeah, and then, as always, net torque, not as always, but for a static problem, the net torque is going to be 0, net force is going to be 0. So, what do we have torque from? Well, we've got the mass of the car times G times the distance it is from the axis of from our chosen pivot point, and that's acting at 90 degrees. Then we've got mass of the bridge times G, acting at its distance from the pivot point, and then those have both caused the board to rotate clockwise. Then this one would cause the board to rotate counterclockwise, so it should have the opposite sign. Actually, it's conventional to call clockwise negative, so I'll make both of these negative. And this one positive. Normal 2 times whatever its distance is going to be. And those add up to 0. Then we can write our net force in the y direction. We've got these two support forces upward, and we've got the two gravitational forces downward, and those have to add up to 0. From there, we can just plug numbers in. So minus mass of the car, 2,000, 9.8, that's 8.5 meters from our pivot point. Mass of the bridge, 17,000, G is 9.8. And again, gravitational force on the bridge, we can treat as acting at the center of mass, length 20 meters, so center of mass is then 10 meters from one end, plus whatever this is, times its distance, which is 20 meters. And then we can calculate away. So we're going to move both of these terms to the other sides. That's a positive 2,000 times 9.8 times 8.5 plus 17,000 times 9.8 times 10 divided by 20. So $91,630 newtons is the force, and that's upward, is the force supplied by this pillar. And then in this equation, we then substitute everything we have. N2, 91630, mass of car times G is 2,000 times 9.8, mass of bridge times G, 17,000 times 9.8. That adds up to 0. Do math. Oops. And we get that that is equal to 94570 newtons, also upward. If they'd been downward, they would have come out negative in our calculations. Here's another example. We've got a ladder leaning against a wall. Okay, and there's no specifics given, just write equations. So we're going to have to introduce some variables. So here's our ladder leaning up against the wall. I'm going to say the ladder has length L, and I'll say it's this angle here is theta. So what forces are acting on this ladder? Well, the ladder has some weight. So you've got the mass of the ladder times G acting in the middle. We'll say it's a uniform ladder. And then it's in contact here. Well, when this is in contact, we've got a normal force that's perpendicular, normal from the ground, perpendicular to the surface. We also have a frictional force. If there was no friction, the bottom of the ladder would slide outward, because this would slide down, slide outward, which means that there must be some frictional force holding it in place, friction from the ground. And over at the wall, they're in contact, so there has to be a normal force perpendicular to the surface, normal from the wall, and a frictional force. If there was no friction, what would this do? It would fall, so there must be an upward frictional force with the wall. Okay, I'm going to write my force equations first. They're going to be easier. To the right, we've got friction from the ground. To the left, we just have normal from the wall. Those add up to 0. In the vertical direction, we just have friction from the wall up, normal from the ground up, and gravitational force down. Okay. Now the torque equation is a little bit tricky, but we can still work it out. Again, the pivot point, we could set it any place we wanted to, but the best place to set it is where we can get rid of forces. I will choose to set it right there, down at the bottom of this ladder. So then we've got torque from mg, and that would cause this ladder to rotate clockwise, so I'll call that negative. That acts a distance, half the length of the ladder, L over 2 away. And what's the angle we've got? Well, this angle here is theta, which means that this is the complement, which is 90 minus theta. Okay, so we got that. We've got this normal from the wall. That would cause the ladder to rotate counterclockwise. So plus normal from the wall. That's a distance L away from our pivot point. And this is theta. This angle is also theta by alternate interior. So that's just times sine of theta. And we've got friction from the wall. Pushing up, that would also cause the ladder to rotate counterclockwise. That's plus friction wall. That's also acting a distance L away. But then what angle does this one make? Well, this right here, this is 90, this is theta, so that this is theta, and these two here are vertical angles, which means this is theta, which means this is 90 minus theta. So that makes an angle of 90 minus theta to the wall. And we can simplify this expression a little bit, because sine of 90 minus theta, that's a trigonometric identity, that's actually just cosine theta. So 1/2 mgl cosine theta plus normal wall L sine theta plus friction wall L cosine theta equals 0. So those are our equations. Depending on how the problem was stated, we might also be able to use the relationships between normal force and friction. If it was phrased so that there was the maximum static friction, you could say friction from the wall is equal to mu s times normal wall. Friction from the ground is equal to mu s times normal from the ground. Or if it was started sliding, then you could use the same relationships, but for kinetic. Yeah. So those are also relationships that you might be able to use, depending on the situation.